Hello everyone, we're going to be looking at a problem on moments about an axis today. We'll first draw the problem, and then we will look at what kind of questions the problem is asking of us. So we start off with the Cartesian coordinate system in 3D. So I have the x, y and z axes as follows. So the z and the y, and I have the x-axis here. Alright. So x, y and z, and then we have a door-like structure which is held partially open by means of some kind of a cable. Before drawing the door in color, I'm going to draw it in pencil, and then we're going to color on top of that. So here is the idea. So I have a door. The dimensions of the corner points will be given to us as well once we finish drawing the figure here. Alright, so this is held open by means of a cable, and the cable, as you will see, will be running from one of the corner points. We'll call that point as the point A, all the way onto a point on the ZY plane. Alright. Right, so here we have the door-like structure for us. And I'm just shading the corners of the doors and the lines that make up the axis. I have the hinged axis here. So the door is hinged about the y-axis. Let's draw the hinges there. Alright, so here are the hinges. And then let's start labeling some of the points. This is going to be called as point D. This is point A, and then I have this corner point here as the point C, and then I have the origin as the point O. There is a force that runs from the point A all the way to a point B on the ZY plane as follows. Right, so this is some kind of a cable here, and all the way from the point A to the point B. I have this force running along this kind of a cable, and the magnitude of the force is given to us as 30 newtons, and it's directed from the point A onto the point B, which I'm going to mark now. Alright, so I have a force that is running along this particular line here, and the magnitude of that force is 30 newtons. Now for some dimensions for the points that we have under consideration. So here is the door. The length of the door and the width of the door are given to us. So this is going to be the distance from the point A to the point D is given to us as 500 millimeters. Then distance from point A to point C along the hypotenuse is given to us as 300 millimeters. Now notice that if I look at the line OD, it makes an angle with the x-axis. So just completing the following triangle gives us a better idea of what it could be. Look at this. I'm going to draw a line parallel to the z-axis from the point D. That's going to intersect the x-axis at a certain point, and we are given this angle here as 30 degrees. And the point O and the point C are parallel to the point D and A, the lines joining those 2 points. Alright. Okay, so here is the basic idea. We have a force running from the point A to the point B, and then I have the hinged axis of the door is actually the y-axis, or the line from point O to point C. And distance from D to A is 500 millimeters, distance from A to C is 300 millimeters, and you see that the door is held slightly open from the XY plane. It is falling a little below the positive XY plane, so the Z dimensions for some of these points will be negative, especially for the point D and point A. And the angle that it is held open by means of this cable is given as 30 degrees. Alright, what do we need to find? We need to find two things. We need to find the moment of the force of 30 newtons about the hinged axis, and we also need to find the moment of this force about a line joining the point D and C. Alright, find moment of the force of 30 newtons about, first of all, the hinged axis, and about a line joining points D and C. And for each part of the problem, we need to express the answers as Cartesian vectors. And we will make use of the vector approach for these problems. My rationale behind using the vector approach, even though this does not seem quite obvious, is that whenever you see things in 3D, it is always safer to use the vector approach because the math takes care of itself. But the scalar approach is of course more intuitive and will help us in develop a better reasoning in terms of how the rotations are produced. Alright, excuse me. So there are two lines that are of interest to us here. The first is the hinged axis, which is a line joining the point O and the point C, and then a second line is a line joining the point D and the point C. And before that, before we start proceeding with anything, we need to look at the points that we are interested in here. First of all, the dimensions for point B, we will write that down as follows. The point B is on the ZY plane. This is given as a distance of 150 millimeters along the positive Y, and then the height of point B along the positive Z direction is given as 250 millimeters. Alright, so the points of interest for us are the point A and the point B, obviously, because the force is aligned along that direction. Then I also have the point D and the point C and the point O. The point O is an obvious choice because it is the origin, and it's always useful to know the coordinates of the origin, and perhaps the easiest point to write out as well. So my points of interest are the point A, the point B, point C, point D, almost alphabetically. These are my points of interest, and so my first order of business will be to write down the coordinates of each of these points of interest. Alright, so let's write down the coordinates of each of these points, and towards that we will look at the figure drawn in a slightly more easier manner as we go on through the problem. Alright, so if I look at the coordinates of the point O, so the coordinates of the point O will be 0, 0 and 0, so that's easier to write. So many millimeters. And then we look at the coordinates of the point C. Coordinates of point C is fairly straightforward to write because it's a point on the y-axis. It's at a distance of 500 millimeters from the origin, and we're going to write the units in terms of meters and not millimeters, so I'm going to write this as 0.5 meters along the positive y direction. Alright, so coordinates of point C will be 0, 0.5 and 0, so many meters. Then we can write the coordinates of the point B as well. Look at the point B. The point B is a point on the positive zy plane, which means it does not have an x dimension. Along the y-axis it is at a distance of 150 millimeters, and along the z-axis it's at a distance of 250 millimeters, which means we're going to convert these into meters. Alright, so coordinates of point B are going to be 0 along the x-axis, as you can see, and then it's going to be along the y-axis 0.15, and then along the z-axis is 0.25 meters. Then we need to come up with the coordinates of points D and point A respectively. So now these are going to be slightly more involved because they are at an angle here. If we start off with the coordinates of point D, as you can see here, the point D, in order to reach the point D, I have to travel a certain distance along the positive x-axis, and I have to travel a certain distance along the negative z-axis. I know the length of the hypotenuse here is going to be 300 millimeters, which is the same as that, which means that if I look at this triangle here, this is a right angle triangle in there, and if it's a right angle triangle, the angle is 30 degrees, then the hypotenuse length is 300 millimeters or 0.3 meters, and so this is going to be 0.3 times sine of 30, and that's 0.3 cosine 30. Alright, so this is going to be 0.3 sine 30, and then this distance here is going to be 0.3 times cosine of 30. So you can see for the point D, there is a distance along the positive x direction, which is 0.3 times cosine 30. There is no distance along the y-axis, and there is a distance along the negative z-axis, 0.3 times sine 30, as you can see below here. Alright, so coordinates of point D are along the positive x-axis I have 0.3 cosine 30. It's on the y-axis, so 0, and then minus 0.3 sine 30, so many meters. We will simplify this. 0.3 times cosine 30 will give you 0.26, and minus 0.3 times sine 30 is going to be minus 0.15, and so the coordinates of B will be 0.26, 0, and minus 0.15, so many meters. And then lastly, we look at the coordinates of point A. Now point A and point D, as you can see, they share pretty much the same x and the z coordinates, and the only thing is point A is at a distance of 500 millimeters along the positive y direction, and you can take a look at this by extending this line here. If I join the point A and the point C, you get a similar kind of a right angle triangle there. The angle here is also 30 degrees, and so the coordinates of point A will be the same as the coordinates of point D along the x and the z axis. So along the x axis is going to be 0.3 times cosine 30, along the z axis it's going to be negative 0.3 sine 30, and then I'm going to have something along the y-axis which is positive 0.5 meters or 500 millimeters for the point A. Alright, so for the point A, we have the following. Coordinates of point A will be 0.26, and then 0.5, and then minus 0.15 meters. Alright, so we have the coordinates of all the points of interest, and just to very briefly look at these things again. Coordinates of point O, 0, 0 and 0, that's fairly easy to see. Coordinates of point C, if you can see that, point C is a point on the y-axis, which means that it has a coordinate only along the y direction, so that's 0.5 or 500 millimeters. And then look at the coordinates of the next point, which is the point B here. Look at the coordinates of point B. It's on the zy plane, and so this is going to be 0.15 meters along the positive y direction, and then 0.25 meters along the positive z direction, nothing on the x-axis. Then I come to the coordinates of point D, slightly more involved point here. If I look at the coordinates of point D from the picture we've drawn, we have this right angle triangle. There are actually two of them there, so here is one of the right angle triangles, and then here is actually the other one, which is useful for the point A. So if you look at this right angle triangle, the point D is sitting on the positive x-axis and on the negative z-axis. And the coordinates are 0.3 cosine 30 along positive x and 0.3 sine 30 along the negative z, and that's what we have written here. 0.3 cosine 30 is 0 and minus 0.3 sine 30, or we simplify this and write this as 0.260 and minus 0.15 meters. And then lastly we come to the point A. Look at the point A. To reach the point A from the origin, I travel along the positive y-axis by a distance of 0.5 millimeters. Then I travel along the positive x-axis by a distance of 0.3 cosine 30. And then I travel along the negative z-axis by a distance of 0.3 sine 30. And so point A shares the same coordinates as point D along the x and the z-axis, but is at a distance of 0.5 meters along the y-axis. And we have those coordinates written down here for the point A. Alright, so we have all the coordinates of interest for us, and the next step is obviously what is the use of all of these coordinates. We go back to our figure here. When you look at the figure here, we see that the direction of the force is going to be from the point A to the point B, as the force is directed that way in the figure. So which means that if we have to write the force as a vector, the magnitude of the force is known, we need to find the unit vector along this particular line, which is going to be the unit vector from the point A to the point B. Alright, so let's write the unit vector from point A to point B and then write out the force. So force FAB is the magnitude times the unit vector. Unit vector is nothing but the ratio of the position vector to its magnitude. And so if I write out this force, so FAB is going to be, the magnitude was 30 newtons, times the position vector from point A to point B, the coordinates of the last point minus the coordinates of the first point. So coordinates of B, which is right there, and coordinates of A, so coordinates of B minus A, so that's going to be 0 minus 0.26, so that's minus 0.26 in the I, and then this is 0.15, and then this is 0.5, and so this is going to be 0.15 minus 0.5, or minus 0.35 J, and then I'm going to have 0.25 for B, minus 0.15 for A, coordinates of B minus A, so 0.25 minus minus 0.15 is plus 0.4 K, by the square root of the sum of the squares of these quantities. If you do that, you're going to get 0.59, and so the force FAB can be written as a vector eventually as follows. So force FAB written as a vector, we will copy down this information in the next page as well. So this is going to be minus 13.2 I minus 17.8 J, and then this is going to be plus 20.3 K, so many newtons. Alright, so we have all these coordinates, we have the force written as a vector, and now we need to set about finding the moments about the axes of interest for us. And to do this, we take recourse to the figure that we drew earlier. So I'll draw a shortened version of that particular figure. So this is the z-axis, this is the y-axis, and here is the x-axis. And then I have the door, which is positioned right here. And then the hinged axis, which is drawn right there. And then I have a line joining the point A to the point B, which is where the force is running through. So point A and point B. So this is A, this is B, this is first of all the y-axis, the x-axis, and the z-axis. Here is the origin, and then here is the point C, and then here is the point D. Alright, now we just want to set up the basis for finding moments about both the axes of interest that we are asked to find the moments about. So first of all, the force is along the line from A to B, so the force is in this particular direction. So this is going to be the force F AB. Now we look at the first line of interest. You see that the first line of interest is the line from O to C, which is the hinged axis here. And so in order to find moments about an axis or a line, I always choose a point on that line first. And so I can choose a point on that line. I can choose point C as a point on the hinged axis. Alright, so we choose a point on the line of interest. Now there are two lines of interest for us because there are two parts to this problem. So for the first one, about the hinged axis, I choose the point C. Now automatically I also am interested in, so the line that we're interested in, the first line is the hinged axis, right there. Then the second line that I'm also interested in is the line joining the point D and the point C. Right, and you see that I can either choose the point D or I can choose the point C, and of course for the hinged axis I can either choose the point C or the point O. I decide to choose the point C. This is because when I look at the second part of the problem, I'm asked to find moments about this line as well, the line joining the point D and the point C, and for that as well I see that point C is a point on that line. So that's what is going to be justifying my choice of the point C here. So about the line CD, choose the point C. Alright, so C is my point of interest on the line of interest. And so what is my next step? My next step is to find the moment of the force FAB about that chosen point. Okay, so that's what we're going to do. Then find moment of the force FAB about the chosen point, which is the point C. How do I find moments? All I have to do is from the point of interest I can take a position vector to any point on the line of action of the force. So the line of action of the force passes through the point A and the point B. So I can either choose point B or I can choose the point A. I decide to choose the point B for this one here. So my position vector is going to be from the point C to the point B. So I'm going to be drawing it here. So this is going to be my position vector, and it's going to be RCB. It is always from the point of interest to any point in the line of action of the force. You can also choose the position vector from the point C to the point A. That is also a perfectly valid choice. You could also do RCA, but it's always from the point of interest to any point in the line of action of the force, which means that moment about the point C is RCB across to the force, and equivalently this is also RCA across to the force FAB, whichever is easier for us to compute. And I'm going to compute RCB because I like the point C and the point B. Alright, so we have the coordinates of the point C, we have the coordinates of the point B, and we also have the force. So all we have to do is start computing these values now. So from before, I have the force FAB, and this was written as minus 13.2I minus 17.8J plus 20.3K, so many newtons. Then coordinates of point C from before was 0, 0.5, and then 0, so many meters. Coordinates of point B were the following. It was 0, and then it was a point in the positive zy plane, so 0.15, and then 0.25, so many meters. And so my RCB is going to be coordinates of B minus the coordinates of C, and I'm going to end up with 0I, then I'm going to have minus 0.35J, and then plus 0.25K, so many meters. And then I set about finding the moment of the force F about the point C. And for this we have the cross product. So moment of the force about the point C. The force of interest for me is the force FAB. I have the cross product, so this is going to be I, J and K, the first row of this cross product, which is given by the determinant here, and the second row is from the coordinates of these things, the position vectors, so 0, minus 0.35, and then plus 0.25, and then the third row of the determinant is given by the terms of the force vector, so that's minus 13.2, minus 17.8, and that's 20.3. And so if we compute the moment, let's do this very quickly. Force FAB, this is going to be I times the minor, which is obtained by covering the row and column corresponding to I. So this is going to be minus 0.35 times 20.3 minus 17.8 times 0.25 minus J times a similar such minor, that's going to be 0 times 20.3 minus 13.2 times 0.25, and then I'm going to have something in the K direction as well here. It's going to be 0 times minus 17.8 minus 13.2 times minus 0.35. Alright, we can compute this determinant by crunching these numbers, and we get the following answer for the moment about the point C. Alright, so moment about the point C. After we go through the calculation, this is due to the force FAB is going to be minus 2.7 I, then I'm going to have minus 3.3 J minus 4.62 K, and this is going to be so many Newton meters. Alright, so this is the key step here in finding a particular point of interest, and then we find the moment about that particular point, and then the next step is to look at the line of interest and decide how to find the moment about that particular line. Now towards this, let us once again very quickly redraw the problem so that we know what the lines of interest are, and then we can look at how to compute the moments about these lines. So I have my x, y and z axes, and then we have the door which is drawn here. This is the hinged axis of interest for us, and we also have the force vector. So first of all, this is the z, this is the x, and then this is the y. The force vector, as you can see, goes from the point A to the point B, point A to point B, and then the force vector is F AB, this is the point O, this is the point C, and then I have the point D, and then I have two lines of interest here. One is the line joining the point O and the point C, which is the hinged axis for me, and then another line is a line joining the point D and the point C. Alright, so these are both lines of interest for me. and I need to find the moment of the force about that particular line of interest. And how does that get done? We already have a moment about a point on that particular line. So let's consider, for example, the hinged axis, which is the line OC. I already have a moment about a point on that particular line. So if I have to find moment of the force about that line itself, then all I have to do is take the moment that I just computed here and then dot it with the unit vector along the line of interest. Alright, which means that moment about the hinge, if I want to look at the magnitude, this is going to be equal to the dot product, in this case the magnitude of the dot product between the unit vector along the line of interest, which is a line OC. So this is going to be unit vector along the line OC dotted with the moment about the point C, which we just found out. And then likewise, if I need the moment about the line CD, then the magnitude of that moment about the line CD is going to be the dot product of the unit vector CD dotted with the moment about a point of interest on that particular line. You see, I could have either chosen point D or point C. I chose point C because this was a point on both the lines of interest. And then the next step would be to do the actual dot products. This is fairly straightforward. And then we will also have to write the moment as a vector itself. And for this, we just want to be slightly careful here. Now look at what the sense of the moment is going to be. So for example, I have the line FAB and then I have the line OC here, right? So I use the right hand rule. I align my fingers along the line of action of the force. You see my palm is going to be facing the line of interest, which is the line OC. If I curl my fingers, you see the direction of my thumb is pointed from the point C to the point O, which means that the direction of the moment about the line or about the hinge is going to be actually directed from point C to the point O. And so you see, this is going to be the direction of the moment about the hinged axis. And likewise, if I look at the moment of the force FAB about the line joining the point D and the point C, if I use the right hand rule, my fingers are aligned with the line of action of the force. My palm, you see, is facing the line joining the point D and the point C. If I curl my fingers, you see the direction of my thumb is pointed from point C to point D, which means the moment about the line DC is directed from the point C to the point D. And just to look at this, so this is going to be the direction and the sense of the moment, and this is going to be moment CD, which means that if I have to write each of these moments as a vector, then for the hinged axis I need the unit vector from C to O, and for the line joining the point D and the point C, I need the unit vector from C to D, which means that if I write these as vectors, then M hinge is the magnitude, which we just find from the above thing, times the unit vector from which line, which point to which point. It's going to be from C to O, because that's the direction of the moment vector. And likewise, we will write this for MCD as well. We will look at this from a slightly better perspective in the next figure. Alright, I'm going to rewrite the moment that we just computed earlier on. So moment about the point C, due to the force FAB, we can lose the subscript on the force because there is only one force here causing a moment. So this is going to be minus 2.7I minus 3.3J, and this is going to be minus 4.6 K, so many Newton meters. Alright, so we can write out the answers as follows. So moment about the hinged axis, magnitude is going to be the dot product of magnitude of the dot product from O to C about the line of interest, dotted with the moment that we just found out from above. And then if I have to write this as a vector, then M hinge is going to be u from C to O times the magnitude of the moment that I just found out from the previous step, and then likewise magnitude of the moment about the line CD is going to be the dot product of these two quantities, and then moment written as a vector is going to be the unit vector times the magnitude that we just found out in the previous step. And we can write out the unit vectors and so on and so forth. Now in this case itself, instead of writing it as UOC, I can write this as UCO in this step on top here, because I'm just looking at the magnitudes only. It makes no difference to us. So if we look back on here, I can have the unit vector along CO. You basically see that this is going to be in the negative y direction, because I'm going from point C to the point O rather than point O to the point C. So UCO is minus J. And then we have UCD. You see that we need unit vector from C to D. This is because of the right hand rule applied for the moments, lines of line of action of the force coincident to the fingers of the right hand aligned in that direction. My palm faces the line or the axis of interest. I curl my fingers, look at the direction of my thumb, it's directed from point C to point D. So that's going to be the direction of the moment, and the sense of the moment is curling about that particular line. So I need UCD. So UCD is the position vector by the magnitude of the position vector. We have all of these quantities from before. We have coordinates of C and D earlier on. So this is from the previous page. I have the coordinates of C and the coordinates of D, and if I do the math for these, I get the following. It's going to be 0.26i, then minus 0.5j minus 0.15k divided by the square root of the sum of the squares will give me 0.583. So I have everything. I have the moment about the point C as well, so all we have to do is compute the answers. So let's start off with the moment about the hinge. So magnitude of the moment about the hinge is going to be the dot product of the unit vectors, magnitude of that about the point C. So this is going to be the magnitude of this. It's going to be minus J or plus J, does not make a difference to us, dotted with the moment that we just found out earlier on. So 2.7i minus 3.3j minus 4.6k, magnitude of that, and if I do the dot product I end up with only 3.3. And so the magnitude of the moment about the hinge is going to be 3.3 Newton meters. But if I have to write this as a Cartesian vector, then m hinge is its magnitude times the unit vector from C to O, as we have discussed before, and this is going to be minus 3.3 J Newton meters. And once again, why is it the unit vector from C to O and not O to C? This can be very easily seen from the following figure. I have the XYZ coordinate system, and then I have the door which is drawn below, and then I have some line of interest and so on, and I have the line of action of the force. So here is the force from the point A to the point B. The force is directed this way, so FAB, and then I have my line of interest or axis of interest, which is this line here, because that's containing the point O, the point C, and of course the hinge as well. And as you can see, if I have to find the moment of the force about a particular line of interest, right hand rule, fingers of my right hand aligned with the force, my palm faces the line of interest, I curl my fingers, and you see that my thumb is pointed from the point C towards the point O, and so that's going to be the sense of the moment. This will be marked here, and that's going to be M about the hinge, and it's going to be clockwise about the positive y-axis. If you have a person who's sitting here and viewing it, for that particular person the sense of that moment will be clockwise about the positive y direction. And likewise we can find out the moment about the line CD. Last step towards finding that answer is as follows. So I have a moment about the point C already known to me. So magnitude of the moment about the line CD is magnitude of UCD dotted with the moment about the point C, and this is going to be the dot product of these two. We already have UCD as follows. We wrote it in the previous page. So this is going to be 0.26I and then minus 0.5J minus 0.15K divided by the square root of the sum of these squares, dotted with the moment that we found out, which was minus 2.7I minus 3.3J minus 4.6K. And we're looking for the magnitude of this one without considering any of the signs, and then if you do the dot product, this is going to be giving you the following answer. This is approximately 2.8 Newton meters, and then if you want to write it as a vector, MCD is the magnitude times the unit vector, and so MCD is essentially 2.8 times the unit vector UCD, which is written here, and then once we do the math, you're going to get 1.25I minus 2.4J minus 0.72K, so many Newton meters. And once again, why is it directed along CD and not DC? We will convince ourselves with this really quick figure here. X-axis, Y-axis, and Z-axis. I have the door, and then I have the force from the point A to the point B, as I have drawn here, point A to point B. Here is the direction of the force vector, and then I have the line of interest, as you can see, is from the point C to the point D. So here is my line. This is the line about which we need to find the moment of this particular force. And so if I use a right hand rule, fingers of my right hand aligned with the force FAB, my palm faces the line of interest, which is a line CD or the line DC, and no matter how we call this. If I curl my fingers, look at the direction of my thumb. The direction of my thumb is pointed from the point C to the point D, so it is directed along CD, right? And so this is going to be the sense and the direction of the moment. So this is going to be MCD, as we have found out in that case. Alright, thank you very much.